Okay, I'm going to talk you through the proofs for the weekend's homework. And the first one was number 4, which is Theorem 519, and different proof of it. And it's proving that the median of a trapezoid is A, parallel to the bases, and its length is equal to the average of the two base lengths. Okay, so I'll start by finding the coordinates of the median, of the endpoints of the median. And it's going to be the midpoints of the two sides. And one of them is right here. And it's at the coordinate b over 2, comma, c over 2. And the midpoint of this side of MP is the average of the x values and the average of the y values. So it's d plus a over 2, comma, c over 2. Now, I mentioned in the email, if I were making this, if I were doing this on my own and weren't using the diagram that they had here, I would make all those coordinates twice as big. I would make them all 2b, comma 2c. I'd make m 2d, comma 2c. I'd make p 2a, comma 0. That way, when I found the midpoints, I wouldn't have these fractions. It's up to you. I prefer actually to make everything twice as big if I know I'm going to be finding midpoints. But I'll go with what this diagram has here, and I'll do the problem as is. But feel free to make everything twice as big. Okay, so part A, prove that the median is parallel. Well, first, we'll just compute a few slopes here. So the first slope, the slope of mn. And the slope of mn is the rise, which is c minus c, over the run, which is d minus b, which turns out to be 0 over d minus b, which is 0. The slope of, we'll call this, give the median a name, xy. Draw it in there. The slope of xy is, well, the change in y is c over 2 minus c over 2, and the change in x is going to be d plus a over 2 minus b over 2. And it doesn't really matter what the denominator is because it's going to be 0 over something, which is just 0. And finally, the slope of OP, is equal to the change in y, which is, it's 0 minus 0 over the change in x, which is a minus 0, which is going to be 0. And I'd say, therefore, the slope of mn is equal the slope of xy is equal the slope of OP, and therefore xy is parallel to mn is parallel to OP. So there's the first part, and how you can write it out. The one thing I should have said earlier was by the slope formula. By the slope formula. I'll cite the formula I'm using, by the slope formula. So by the slope formula, these are the slopes, and since they're all 0, it means that they're all equal, and since they're all equal, then those lines are parallel. So there's part A. Okay, now for part B, we want to show that the length of the median is equal to the average of the two bases. So this is where I want to use the distance formula. And I said in the email that you can cite the distance formula, so you can say by the distance formula. But you don't have to actually do the formula out if the line is horizontal or vertical, because you know what it'll come out to be. For example, the length of mn is going to equal, well, you could write out, if I wrote out the distance formula, this is what it would be. It would be the square root of the change in x's, which is b minus d, squared, plus the change in x, which is change in y, c minus c squared, which comes out to the square root of b minus d squared, which turns out to be the absolute value of b minus d. Which in this case, because it's clear that d is bigger than b, this would equal d minus b, which would be the positive value. But you don't have to do this in a formula, because this same sort of thing is going to happen every time if it's horizontal and vertical. So you're totally fine to say something like this, that xy is equal to, well, the change in, it's basically just going to be the change in x, which is d plus a over 2 minus b over 2, which can be simplified to d plus a minus b over 2. And finally, OP is going to be just the length there is a. Now, to prove that it's equal to the average of the bases, well, the average of the bases is going to be OP plus MN over 2. So I can say, once I've proven all this, I can say, therefore, OP plus MN over 2 equals, well, it's going to be A plus MN, which is D minus B, over 2. And that equals XY. And there's my proof. Okay, the next proof was prove that a quadrilateral formed by joining in order the midpoints of the sides of an isosceles trapezoid is a rhombus. Okay, so the first thing I need to do is to draw an isosceles trapezoid. And I also know that I will be finding midpoints. So what I'm going to do is I'm going to make all the points have 2 in front of them, so I can easily find a midpoint. So let me draw this in. So draw an isosceles trapezoid. And this is just one isosceles trapezoid. I'm going to put this coordinate here at 2a, comma 2b. And I'll put this one here at 2c, comma 0. And because of the symmetry that this thing has, the change in x here should be the same as the change in x here. So this distance here was 2a, so this distance here should be 2a, which allows you to say that this coordinate here is going to be 2c minus 2a, comma 2b. Same y value. All right. And we'll give this a name. I'll call it trap. T-R-A-P. All right, so I marked the 4 midpoints of the 4 sides on there, and so I'd first start out by saying, by the midpoint formula, is I'd find the coordinates of these. By the midpoint formula, x equals a comma b, y equals let's see, it is going to be c comma 2b. Z equals 2c minus a comma b, and w equals c comma 0. Now I'm leaving out the work for it, and it's okay. I'm citing the formula, I applied the formula, I'm not going to do the workout for it. You don't have to do the workout on every one of these. If you want to, go ahead. So then I'll draw the quadrilateral connecting these. And how could I prove it's a rhombus? Well, there's a few ways of proving it's a rhombus. If you think back, we could prove that it's a parallelogram and then prove that 2 consecutive sides are congruent. But I think the easiest thing is just to find the lengths of the 4 sides. It's going to be pretty straightforward now that we've got the 4 coordinates. I can say by the distance formula, what's going to happen here? Well, xy is going to equal the square root of, well, from x to y, so here's x and here's y, it's going to equal 2b minus b squared plus c minus a, comma squared, which equals the square root of b squared plus c minus a squared. All right, so there's the length of one of the sides. And all I have to do is now work through the other sides and show that they're all the same thing. So the next one I'll say is xw equals the square root of, and xw is going to be, well, a change in x, which is going to be c minus a squared plus the change in y, which is 0 minus b squared. And that's equal to the square root of c minus a squared plus b squared, which is the same thing. Create more room. And let's see, wz is equal to the square root of, wz is going to be, well, the change in x is going to be 2c minus a minus c squared plus the change in x, which the change in y, which is b minus 0 squared, which simplifies to c minus a squared plus b squared. And finally, yz is equal to the square root of, well, y to z, it's going to be 2c minus a minus c squared, sorry for my handwriting, and then plus b minus 2b squared. And so this simplifies to the square root of c minus a squared plus negative b squared, which is b squared. And I could say, therefore, wz equals yz equals xy equals, whatever I said here, xw. Therefore, w, x, y, z is a rhombus. And there's the proof. All right, here's a proof I love, and I love it because if you were to prove this with non-coordinate geometry, it would be a really, really tough proof. But with coordinate geometry, it's not too bad. All right, so I'll start out with generic parallelogram. And I'm not going to be finding midpoints of anything here, so I will just make them, very generic points. So I'll put one point at 0, 0. I'll put this point here at a comma 0. I'll put a point here at b comma c. And then this point here will have to be at b plus a comma c. And why does it have to be there? Well, because this length here is a. And since this x-coordinate here is b, I then need to go over a from there. And that puts me at b plus a for the x value, and the c values of these two coordinates, the y values both have to be c. All right, so let's give this a name, these coordinates some names, and we'll call it a, b, c, d. So now we just have to find a bunch of distances. And I'll say by the distance formula, AB equals the square root of, well, it's going to be b squared plus c squared. And BC is going to equal, well, it's just a. And I'm skipping that work because you can do that. CD is equal to, well, we can use the distance formula, but we'll see, when we use it, we'll see that it's actually the same thing as AB, and then AD is equal to AD. AD is equal to, let me erase that. AD is equal to A. And then the diagonals, well, BD is going to be the square root of B minus A squared plus C minus 0 squared. And AC is going to equal the square root of B plus A squared plus c squared. C minus 0 squared. All right. So now let's prove what we have to prove here. So what do they want us to show? They want to show that the sum of the squares of the lengths of the sides is equal to the sum of the squares of the lengths of the diagonals. Okay. So what they want us to show is that AB squared plus BC squared plus CD squared plus AD squared is equal to the sum of the squares of the diagonals. Well, let's first find this out. So AB squared is going to be B squared plus C squared plus BC squared is going to be A squared. CD squared is going to be B squared plus C squared. And AD squared is going to be A squared, which simplifies to 2A squared plus 2B squared plus 2C squared. And then the sum of the squares of the lengths of the diagonals, well, that's BD squared plus AC squared. And that's going to equal B minus A squared plus C minus 0 squared plus, well, that's 1, that's BD squared. And then the AC squared is going to be B plus A squared plus C squared. And if I simplify this, this is B squared minus 2AB plus A squared plus C squared plus B squared plus 2AB plus A squared plus C squared. These cancel nicely, and if I simplify like terms, I get 2A squared plus 2B squared plus 2C squared. Aha, so therefore, you can see I've kind of already proven things here, but therefore I can say the finale, which is that A squared plus B squared plus C squared plus A squared is equal to BD squared plus AC squared. And write a little QED, because that is the proof. All right, finally, this proof here. Prove that the diagonals of a rhombus are perpendicular. All right, well, they start here. If you use their hint, and you can use their hint, you can also create your own generic rhombus. I'll use their hint. I'll go along with what they say here, but there are multiple ways of doing this. So we'll start out. We've got the 4 coordinates: 1 at 0, 0. 1's at A, 0. 1's at B, C. And 1's at A plus B, C. And you might be thinking, how is this different from a generic parallelogram? Well, right now it's not. But what we do know is if this is a rhombus, we know that the length of one side is right here. It's A, which tells us that if I thought about this little right triangle here, this side would have B, this would have C, and this would be A. And this side's A, and this side's A, which tells me that C squared plus B squared would have to equal A squared by the Pythagorean theorem, or by the distance formula. You could do it either way. And actually, I'll cite the distance formula. By the distance formula, I'll call this X, Y, Z, and W. That XY has to equal A, which is equal to the square root of B squared plus C squared. So A squared equals B squared plus C squared. Okay, now I want to show the diagonals are perpendicular. Well, let's find the slopes of the two diagonals. And we can show that they're perpendicular if we can show that if their slopes multiplied to -1. So the first slope, so I can say by the slope formula, the slope of xz is equal to, well, the change in y, which is c, over the change in x, which is a plus b. Likewise, the slope of wy, the other diagonal, is going to be the change in y, which I could say is c over b minus a. And if this is true, I can say, therefore, the slope of xz times the slope of wy is equal to the product of these two. So it's c over a plus b times c over b minus a, which multiplies to c squared over b squared minus a squared. Now, how is that helpful? Well, I do know what b squared minus a squared is, because I know what this is. And b squared minus a squared is going to equal negative c squared. So I can say, therefore, which is equal to, equal to c squared over negative c squared, which is equal to negative 1. Therefore, xz is perpendicular to wy. And there's my proof. I hope that these videos helped you understand these proofs a little bit more, and how powerful this coordinate geometry can be. We saw, because we've proven a bunch of these already using other methods, but in some ways this coordinate geometry, if you know the distance formula, the slope formula, and some properties of those, you can find these proofs pretty quickly, and you can get right through them. All right, so hope that helps. Thanks a lot.